Welcome to the Cave of Science, and this is our video review of part one. First one I did was too long of a video. I tried to do them both together, so we're going to split this thing in half. On part one, the first question we had is to convert the stuff we were talking about, local time to UTC and vice versa. When we have local time, the first step we got to do is convert it to military time, and 6 p.m. is converted to 1800 hours. And we want to go to, we're in Eastern Standard Time. And so we got to add 5 hours because we're 5 hours behind them. So if we add 5 hours, 1800, it's 2300 Zulu or universal time there. If we want to go the opposite way, we are given Zulu or UTC time. And we are going, in this particular case, to Mountain Standard Time. We can see we got to subtract 7 hours because we're 7 hours behind. So 1200 minus 7 is 0500, which is 5 o'clock in the morning. And again, you can make up your own problems with these. We did quite a few. Go back and review that sheet. One thing I want to mention, make sure our answers are in complete sentences. Let's see if I can get out of this a little bit. The layers of the atmosphere. This is pretty much one of the few recall questions on here. Troposphere is where the weather occurs, and we get the tropopause. Then we get in the stratosphere where the ozone layer is. And then we get to the stratopause. Again, the temperature changes. It starts increasing in the mesosphere. We get to the mesopause. That is that change again into the thermosphere. Pretty much a straight recall. This is what you guys graphed, and so I'll make sure you go over that. Yeah, let's see if I can get into this a little tighter. There we go. Explain why climbers ascending really any mountains, but Mount Everest and so forth, would want to bring oxygen. Well, there's just less air in the discussion. You guys did the pressure above sea level, and you found that it decreases. The key here to remember is that the percent of oxygen at 21% remains constant. You could think of it as being 1,000 parts of air at the surface. Well, it's still 21% of 1,000. If you're on the top of Mount Everest and there's only 100, it's still 21% of that 100. The percentages does not change. Now, if we were to look at this in terms of nitrogen, it's 78%. It doesn't matter where in the atmosphere you go, as long as we stay within the lower level, is that you're going to get 78% nitrogen and 21% oxygen. It's just that there's less total air as you go up in altitude. The next question was this whole idea of latent energy. And if we go from condensation, when water condensates, temperature slows down, or excuse me, kinetic energy slows down, the particles lose energy to the surroundings, and that's that latent energy. That's the same idea when water freezes, it releases energy to the surroundings. Now, if you go in the opposite direction, if water goes from the solid and goes into the liquid, you're adding energy to the water, therefore the surroundings will lose. And likewise, we talked about evaporation being a cooling mechanism because the energy, especially when we talk about your body, the energy from your body goes in to evaporate the sweat on your skin. So the water gains the energy, but your body loses. You've always got to account for that flow of energy. The next one dealt with a mid-latitude cycle and a mid-latitude wave, that combination of a cold front, low pressure, warm front. And we know the general track across the midsection of the United States. We are in the prevailing southwesterlies, so the wind blows from the southwest to the northeast. So that's the general track most of the time. The feature that also moves these weather-producing systems across the United States is the jet stream. And this jet stream is also bringing all this cold air, this continental Arctic air from the Arctic Circle down in where we are. And we're going to end up with the coldest February on record. The two air masses, boy, it's that maritime tropical out of the Gulf of Mexico and the continental polar out of Canada. What we're experiencing now is that continental Arctic. And again, at this point you should be able to name the air masses. If they're wet, they're maritime. If they're dry, they're continental. If they're cold air masses, they're going to be polar or Arctic. And if they're warm, they're going to be tropical. That's really all there is to that. From the map, what's most likely wind direction in Comstock Park? Well, you can see it's a low pressure, so it's counterclockwise rotation. So CP is to the southwest, so it looks like the wind's going to come out of the southwest or the south. If this low pressure was to the east with a counterclockwise, it would look like the wind is going to come out of the north. And again, it's just wherever it is relative to where you are. So make sure, again, you got to know your rotations. This problem is pretty much the closer the isobars are together, the higher the wind speed. And I know the map wasn't the best, but you can see Florida down here and right up in the midsection of the country. So we had isobars very close together, so you would have higher wind speed. Where they're farther apart, like in Florida and Texas here, the isobars are far apart, you're going to get lower wind speeds. And again, it's all relative. But that's, we did a couple exercises on that. The table here is comparing tornadoes to hurricanes. Tornadoes mostly are confined to the mid-latitudes. Hurricanes start over in the South Atlantic, pretty much stay there until they get into the Caribbean. Seeing they're both storms, they're low pressure systems, it's going to be counterclockwise rotation. The intensity scale are how they're measured. For a tornado, it's Fujita, and for the hurricane, it's the Saffir-Simpson. In a tornado, the wind causes the most damage, and in a hurricane, it's the flood or the storm surge. Both of them, the winds are measured by an anemometer. Pressure is measured by a barometer. Relative size, tornadoes are relatively small. Hurricanes are really massive compared to the area that a tornado covers. Pressure systems are both low. Seeing there's storms, there's rising air. You have the condensation, that whole release of latent energy. Source of fuel, water vapor. To have a storm, you gotta have water vapor. All right, so hopefully this one helps, and we'll get this one together, and then we'll get the next one published.